Hello and welcome to the 5.4 notes. This is a section about the fundamental theorem of calculus. We call that FTC. This will be a multiple video section. But what I first want to talk about is what we are trying to do. We are trying to evaluate definite integrals. So we want to, the whole point of the fundamental theorem of calculus is to evaluate integrals by hand. Integrals algebraically, okay? Algebraically. Okay, so by hand, all right? And so in order for us to kind of, we could just tell you what to do and it'd be pretty easy, but we want to show you why this works and how we can do this. So what I want to show you is this example, okay? And so we have this graph here. The following graph shows the velocity of a car traveling at a constant rate of 60 miles per hour, okay? And what we want to do is calculate the total distance the car travels from 1 hour to 3 hours, okay? And so, given something like this, all right, this integral here, from 1 to 3 of v of t dt is the same thing as us saying the integral from 1 to 3 of 60 dt. Okay, the reason behind that is that the velocity function, v of t, is a constant function of 60. Okay, so all I did was substitute those values. Now, if we wanted to calculate the area under the curve between 1 and 3, okay, so what I know here is that all of these areas, this area, okay, 1 hour times 60 gives me an area of 60, and then I add another 60 miles to this. So we know that the area under the curve, okay, using geometry, is 60 times 2, okay, which gives us 120. So what I know is that the total distance traveled here is 120 miles, okay? And so that's something that we've done in previous sections, and so we're pretty familiar with that, and I think that this is, more or less a common sense thing at this point. If we're just talking about driving a car at a constant speed, then how far do you go in 2 hours? And we're modeling that as the hours between 1 and 3, okay? And we go a total of 120 miles. So now what we want to do is we want to draw the position graph that would show the total distance the car traveled for the first 3 hours. Okay, so now all of a sudden this is a position graph, okay? We are no longer in a velocity graph. Notice how my time is in hours and my y values are measured in miles, okay? That was different here, okay? Here our time was hours, but then our y value was measured in miles per hour. That's a rate. That's why this is a velocity graph. So I'm going to come here, and what I want to take a look at is I want to know, first of all, how far do I go at 0 hours? Okay, at 0 hours, I've gone a total of 0 miles, okay? And so then the next thing I want to do is say, okay, how far do I go after 1 hour? And we know that we travel a total of 60 miles, okay? Now the question is, how far do I go after 2 hours? And the answer is 120 miles. Okay, and then how far do I go if we've gone for 3 hours? And the answer is 180 miles. And what you get here is you get this graph, okay? And this graph is the equation, and we're going to call this P of t. P of t is equal to 60t, okay? Now, here's what I want you to notice here, okay? How do we get the position function? P of t is equal to the integral of v of t dt. And that's how we get our position function. Now, what I want to do is answer this other question down here. Before I do that, let's kind of write down some points that we've got here. Okay, I know that p of 0, okay, is equal to 0. I know that p of 1 is equal to 60 miles. Okay, I know my position after 2 miles is 120 miles away. okay? And then P of 3 is equal to 180 miles, okay? Now, what I want to do is I want to calculate the difference between the positions between t equals 3 and t equals 1. And what do you notice about this and the integral / area found in part 1? So what I want to do is I want to take the difference between the positions. So I want to find P of 3 minus P of 1. Now, P of 3, based on our graph, okay, is up here, okay, which is 180. So I'm going to write that this is 180 minus P of 1, which was 60. Okay, and this gives me a total distance of 120 miles. Okay, and what you should notice here is that when I took the difference between the positions of 1 and 3, I got 120 miles. When I evaluated my integral and found the area under the curve between 1 and 3, we got the same thing. Now let's think about something here. We're getting the same value, okay, by looking at it two different ways, okay? And, you know, one way is graphically, okay, by doing geometry and finding the area under the curve. And another way is doing it by hand and doing it numerically and figuring out, and we get the same thing. But here's the kick, okay? We have to remember, how do we get P? P is the antiderivative of our velocity. So what this does, okay, this allows us to write a theorem, and it allows us to draw a conclusion here. And this is as simple as it gets, folks. There's no other simpler method of showing you the fundamental theorem of calculus than by showing you this, okay, because this is something that you know and that you understand, all right? So what I want to do is then show you the theorem of how we do this, okay? So the fundamental theorem of calculus, and this is called part 2. The way that the books go is that they always, you know, they have two different parts to this, and they're related, and we'll show you how that all works. But it's easier to learn part 2 first than to learn part 1 first, okay? So let's think about this. Let's let big F of x be the antiderivative of little f of x, okay? And what we want to do, our goal is to calculate the area under the curve, okay? Area under the curve, okay? So let's say that we have this. Let's say we have a graph here between a and b under some function f of x, okay, f of x. And if we wanted to calculate that area under here, which we don't have any way of doing that using geometry, but we know that we can express that area using an integral and say that that's the integral from a to b of f of x dx. Now, if we follow the same method, the same idea that we did here, okay, then we can apply it here. And if we take the antiderivative of f, which gives me big F of x, then I could find the area by taking f of my upper bound b and then subtracting the function of the antiderivative evaluated at a, okay? And this part right here gives us the area under the curve. So it's really not that terrible, but it's just kind of hard to know why it happens, okay? And so, you know, this is something that you do need to memorize here, okay? But the way that we can remember it and do it, okay, over and over and over again, how do we remember the fundamental theorem, okay? We think about driving a car at a constant rate of 60 miles an hour, then how far do we travel between hours 1 and 3? Okay, we know that that's 2 hours traveling 60 miles an hour. We multiply those two, we get 120. Okay, but if we take the antiderivative of our velocity, which gives us 60t, okay? Then what we can do is we can then find those different positions at all those different points, and what we're allowed to do is to take the difference between our positions to calculate the total area under the curve, okay? So just to kind of reiterate this, just to kind of show you the example of what we're trying to do here, with all that information we had, all right, if we were to evaluate the integral between 1 and 3 of 60 dt, okay, then this means that we're going to take our antiderivative, which is 60t, and then we're going to evaluate it at 1 and 3. And this part right here is just some notation, okay? This is just how we take the antiderivative notation for f of b minus f of a, okay? And so what we can do here is then we would say that this is equal to, we're going to take 60 times 3 minus 60 times 1, which then gives us 180 minus 60, which gives us a total of 120 miles, okay? So this is how we do that. This is how we evaluate the area under the curve, but it is a process, and there is some explanation to it. So, hopefully that this makes sense. If you need to rewatch this video because you have no idea what this means, make sure you rewatch it. Make sure you write things down that I'm saying, and we'll go from there. So hopefully this makes sense. Stay tuned for part 2, as I will do a bunch of practice problems to show you what we're doing. So thank you.